大部分都做得不错，可是我想最后一题不太好。最后一题我在后面有写我的解答哦。我在那个书的后面有写我的解答，可是后来我看了，我觉得那个好像不太对，所以我会重写解答。OK， yeah。All right, so in the last lecture, I defined the Weil algebra. And the Weil algebra is going to be an algebraic model of the total space of the universal bundle. Okay. So let G be a Lie group with Lie algebra G. So last time we defined a G differential gradient algebra, okay, for any Lie group G, and it's a differential gradient algebra, so it's got a differential D. And then in addition, I said there were three operations: interior multiplication, the Lie derivative, and then right translation. Now, if you assume that G is connected, then you don't really need that right translation, because the right translation you need in order to define an invariant element. But if G is connected, then an element is invariant if and only if the Lie derivative is 0, right? We proved that before. So let's assume that G is connected. Okay? Then a G differential gradient algebra has two operations. So it has interior multiplication and the Lie derivative. Okay? Well, in addition to the operations that comes from being a Lie differential gradient algebra. In addition to those of differential gradient algebra. Okay? So, in other words, we don't need right translation. So I defined the Weil algebra. G is WG. It's the exterior algebra of the dual tensor with the symmetric algebra of the dual. Okay, and in terms of a basis, so given a basis x1 to xn for the Lie algebra, Then we write the basis in the exterior part as theta, lambda theta 1 to theta n, okay? And then we write the basis for the symmetric part as u1 to un, okay? See, these thetas and the u's, you know, they are in the dual. So usually they would be, in differential geometry, they would be written with superscripts. Okay? But here, because, you know, we are looking at the symmetric algebra in the u's, and that means you are going to raise the u's to some power. So that's why we write the indices as subscripts instead of superscripts, because if you write them as superscripts, then, you know, we will not know whether they are indices or powers or exponents, okay? So that's the Day algebra, and we need to define a differential, and then interior multiplication and the Lie derivative, okay? So we defined the differential last time. D theta k is uk minus 1/2 the sum of c I j k theta I theta j, okay? And that formula comes from the fact that you want the Day map, you know, to be a morphism. So this really comes from the formula for the connection, D of a connection. And then duk is the sum of Cijk ui theta j. Okay? So this was what we defined last time. And Ia of theta k, it's, you apply theta k to A, and Ia of uk is 0. Okay? And then La of theta k is Dia theta k plus Iad theta k. Okay? And so Ia theta k is this. Now that's a constant. So D of it is 0. And then D theta k, just a minute. Yeah, D theta k is this. Okay? Okay, so this may not be 0. Well, then there's plus, okay, Ia applied to this. Yeah, so Ia of this is 0, so then minus 1/2 Ia gives the sum Cijk theta I theta j, right? And then this you can work out because Ia is an anti-derivation. But anyway, I think, yeah, you don't need to work it out, okay? So La is just defined by this formula. So La of uk is Dia uk plus Ia duk, okay? And it will be something. well, this will be 0, and then, but this won't be 0. Yeah, it's actually will be IA DUK. Okay, yeah. So this makes the Weil algebra into a G differential Grady algebra. But actually, to check that it's a differential, to check that the D is a differential, right, you have to check that D squared is 0. Okay? So let's do that over here. Okay, now D is an antiderivation. Okay? So you see, we defined it on these generators, then we extend D to the Weil algebra as an antiderivation. Okay. So if D is an antiderivation, what's D squared? If D is an antiderivation, then D squared is a you see, in general, okay, now, if you have two antiderivations, so here D and iota are both antiderivations, then D iota plus iota D is a derivation, okay? So that means dd plus dd is a derivation, okay? And so 1/2 of dd plus dd is a derivation, okay? So since D is an antiderivation, D squared is a derivation. I mean, you can just check it on say a product. Okay? So this is D, okay, D alpha beta plus. Since it's an antiderivation, when you move D across, you get a sign. Okay. D is an antiderivation of degree 1. Right? And now if you do this again, you get D squared alpha beta plus. Okay, now to move this D across, you have to put in the sign of D alpha, which is one more than the sign of alpha. So it's -1 to the degree alpha plus 1, D alpha, D beta. Okay? And then plus -1 to the degree of alpha. And then you move the D across this alpha. So, so, oh, I see. Oh, I see. So it's another -1 to the degree of alpha. Is that right? Oh, no, just a minute. Yeah, no, first I put D here, right? So I have D alpha d beta, right? And then the last term is minus 1 to the degree of alpha, and then I move d across, so I get another one, minus 1 to the degree of alpha. But you see, these two terms will cancel out because they have opposite signs. So they cancels that. Okay? And then these two minus 1s, they give you plus 1. And so you get d squared alpha beta plus alpha d squared beta. Okay? And that shows that d squared is a derivation. If you start with an anti-derivation, its square is a derivation. Okay? And so because it's a derivation, to show that it's 0, you see, you only have to show that the generators give you 0. Okay? Because everything else will be a product of generators. And this formula shows that if the generators are 0, then the product will be 0 also. Okay? So, so proof. It is enough to check that d squared is 0 on a set of generators, a set of algebra generators of the Weil algebra. Okay? Now, a set of algebra generators is theta 1 to theta n, and then u1 to un. Everything is a sum of product of those, right? Theta 1 to theta n, u1 to un. Okay. Okay. What's another set of algebra generators? Instead of u1 to un, I can also use what? You see, instead of u1 to un, I can write the u's, right, in terms of d theta k and thetas, right? So I can also use d theta 1 to d theta k, because the u's can be written as polynomials in these. Okay. Okay. So let's check that d squared of theta k is 0. Okay. Yeah. Now, if you do it here directly, it's going to be quite messy, right? So let's introduce matrix notation, because we know that this looks simpler in matrix form, right? So in terms of, so we let theta be the sum of theta k xk. Okay. Then this equation, okay, so yeah, d theta is d theta k xk, and so we're going to call uk xk. Okay, so this is going to be the sum of uk xk, and then minus a half sum Cijk theta I theta j xk. But Cijkxk, that's the bracket of xi xj. And then this is just the sum of, so this is bracket sum theta I xi, sum theta j xj. Okay? This is this. And so, you see, this is theta theta. And so d theta is actually just u minus 1/2 bracket theta theta. Okay? This is just like the second structural equation for D of a connection. Okay? All right. And okay, yeah. So that makes it easier to calculate d square of theta. It's the eraser of here. Yeah. Okay. Okay. And so d square theta will be du minus 1/2. Take d of the bracket, so you get d theta theta, and then since theta is a one form, plus 1/2 theta d theta. Okay. And okay, now du, yeah, du is here. Okay. So du is bracket u theta. Okay. Minus 1/2. Oh, okay. And then these two terms you can combine, right? What happens if you interchange the order? Is it going to change sign or not? Yeah, because theta has degree 1, d theta has degree 2. So when you interchange, there is no sign coming from these two alone, but then the bracket will give you a minus sign. So in fact, you'll get minus 1/2 there. So this is what we get. Okay? And then d theta is this, right? So put that in. So you get u theta minus u, okay, theta, and then plus 1/2 bracket theta theta theta. Okay. And these two terms cancel, and then this is 0 because it's a triple product of theta. Yeah. So that's one of the homework problems. Whenever you have a one form and you take a triple product like that, it's 0. Okay. Okay. So this proves that d squared theta is 0. And now, if you apply it to the other set of generators, okay. So this says that d squared theta k is 0. Okay, for all k. That's one set of generators. And then if you use the other set, d squared d theta k, well then this is the same as d squared theta k. So it's also 0. Okay? And yeah, so since d squared equals 0 on a set of generators of WG, d squared equals 0 on the Weil algebra. Okay. Yeah. So this makes the Weil algebra into a differential graded algebra. And that means you should be able to compute its cohomology. Okay. The cohomology of the Weil algebra with respect to D. And it turns out that this cohomology is like the cohomology of a point. So it's R in degree 0 and 0 in degree greater than 0. Okay. Now, in general, how do you prove that the cohomology is 0? I mean, what's the standard way to prove that the cohomology is 0? Pardon? A closed form has to be exact, right? That's what you have to show. But how do you show that? There's a way to show that every closed form is exact. Pardon? Poincare lemma. Yeah. Well, Poincare lemma applies if you have a little open set. In fact, how do you prove Poincare lemma? You see. Yeah, well, okay. So the method is you find what's called a co-chain homotopy. So a co-chain homotopy it is enough to find a co-chain homotopy. So a co-chain homotopy is a map K that goes from the complex to itself of degree -1, okay, such that dk minus kd, dk plus kd is equal to the identity. Yeah, you see, this cochain homotopy is going to be an antiderivation. So if you have, and D is an antiderivation, therefore dk plus kd will be a derivation. Okay? And let's see, you want it to be, oh, just a minute, yeah. Well, okay, so you want this to be the identity. Oh, huh? Uh-huh. Well, okay, no, just a minute. I think.
So we need another cochain which cohomology obviously. And this, which cohomology is this type N. We claim they're homotopy.
Well, we're saying that 1 is homotopic to 0, right? Yeah. Yeah, so suppose you can find such a D, so find such a K, then if Z is a cocycle, then dk plus kd apply to Z, okay? It's Z, because this is the identity. But if Z is a cocycle, dz is 0, then this will give you dkz is Z, okay? So it will show that every cocycle is a coboundary, okay? All right? Yeah. And so we just need to find such a cochain homotopy that reduces the degree by 1. Okay? And now let's write down the formula for D. So d theta k is uk minus 1/2 the sum of Cij k theta I theta j, and then duk is the sum of Cij k ui theta k uj, okay? Now, what we can do is that we can make a change of basis again. So this you call zk. Then you see, yeah. And theta 1 to theta n, okay, is Right, that's a set of generators for the exterior part of the Weil algebra. But then in the symmetric part, instead of using UK, you use ZK. Z1 to ZK. Okay? So this is a set of generators for the Weil algebra. Right? Because ZK can be written as UK, can be written in terms of thetas and u's, but the u's can also be written in terms of the thetas and the z's. Yeah.
I think it's Z1 through
A Zn, that's right. Yeah. Zn. Okay. But the advantage of making this change of basis is that now D is simple to describe, because now d theta k is zk. Okay? And dzk, what's dzk? Well, it's d squared theta k, so it will be 0. Okay? So that's d. And then you define k by, okay, k of theta, k of theta k. Now k lowers the degree, so you should get a constant and just define it to be 0. And then k of zk, define it to be theta k. Okay? So yeah, zk has degree 2, right? Because uk has degree 2. Okay, so I define k that way. And now let's compute dk plus kd. So let's see. Then dk plus kd of theta k is, okay, k of theta k is 0, so d of 0 plus k of d theta k is zk. And k zk gives me back theta k. Okay? And dk plus kd of zk is dk of zk is theta k plus k of d of zk is 0, and d theta k is zk. Okay? Yeah. Okay, so kd plus dk plus kd is the identity on the generators. Yeah, now here I have to say how, that's right, this, I define it on the generators, then I extend it to the Weil algebra as an antiderivation. Okay? So N extend to the Weil algebra as an antiderivation. Okay? And okay, so yeah, so since both D and K are antiderivations, so dk plus kd is a derivation. And that means if, since, what I want to say is that since D and theta, D and K are antiderivations, dk plus kd is a derivation. And so dk plus kd, if you apply it to a product, so let's say you apply it to theta I zj, since it's a derivation, it's going to be dk plus kd theta I, okay, times zj plus theta I dk plus kd zj, and dk plus kd is the identity on the generators, so you're going to get what? 2. 2 theta I zj. Yeah. Okay, so that's not quite what I want, right? Because I want the identity. I want dk plus kd to be the identity, okay? So that means this is not quite the k I want. So I think, okay, let's put a bar here. Okay. All right, yeah. So this K bar is almost what I want, except that it gives me this coefficient. So yeah. Yeah. Let's see. So what should I define K to be? Define K to be no, there's a K body. I mean, so the thing is that, you see, the Weil algebra, it has 2 degrees, right? So the Weil algebra is the exterior power tensor with the symmetric power. And this is graded. So it has a degree, right? I can put it, I mean, it's a sum of all of these for different p's. And here, it's the sum of these for all different q's, right? So the Weil algebra, yeah. The Weil algebra, WG, it's lambda G dual tensor SG dual, but that's the direct sum of lambda P G dual tensor the direct sum of SQ G dual. Okay? So an element in the Weil algebra, it has a P degree and a Q degree. Okay? And now if it's in lambda P, then it's the sum of products of P generators. And if it's here, then it's a sum of products of Q generators. Okay? So if I have an element here and I apply VK bar plus KV bar to it, what is going to be the coefficient? P plus Q. Okay? And therefore, in order to get the identity, all I have to do is to divide by P plus Q. I define K to be 1 over P plus Q of K bar on this component of the Weil algebra. Okay? Then VK plus KD will be the identity provided that, well, you can divide only if P and Q are not both 0. Okay. And so VK plus KD will be the identity on the Weil algebra, okay, except when P and Q are both 0. On the Weil algebra, except in degree 0. When an element in the Weil algebra has degree 0, then P and Q are both 0. And what, so that says I have found a cochain homotopy in degree above 0. Okay? So thus, the cohomology of WG is equal to 0 in degree above 0. And in degree 0, well, I just have R. And so the cohomology is in degree 0 it's just R, right? Because there's, yeah. That's because everything in degree 0, oh, just a minute. Yeah, because in degree 0, it's just constants. Because d of a constant, d of 1 is 0. And there's nothing to make it exact. Okay? Okay, so that calculates the cohomology of the Weil algebra. Okay, we're going to stop here for 10 minutes, and then we begin again. Okay? All right. 黄元雄在不在？哦。